Okay, solved problems for chapter 20. So here we have a Carnot engine, and it's going to be pulling heat from a hot reservoir. That's my TH right there. It's going to be dumping what it doesn't use into the cold reservoir. That's my guy in blue right here. The little black guy is going to represent my engine, and I'm going to be pulling QH from my hot reservoir, dumping the energy that I don't use to my cold reservoir, and I'm going to be doing some work. I know that the efficiency is 0.59, 59%, and I know that the amount of work done is going to be 2.5 times 10 to the 4th joules, and the efficiency is related to the work as well as the heat that it pulls from the hot reservoir, just simply as such. I'm asked to solve for this amount of heat it pulls from the hot reservoir. So quite simply, I can write the heat that it pulls from the hot reservoir to be equal to the work divided by the efficiency, which is going to be 2.5 times 10 to the 4th, that's a 4th, joules divided by 0.59, and I'm going to come up with 4.24 times 10 to the 4th joules after packing that into my calculator there. Now I'm told that the engine exhausts the heat to the room temperature of 20 degrees Celsius, so that's going to be my cold reservoir. Of course, we need to work this guy in terms of Kelvin, so the temperature of the cold reservoir in Kelvin, simply add 273 to that, is going to be 293 Kelvin. Now I know that I can write the efficiency for a Carnot engine to be equal to 1 minus the temperature of the cold reservoir and the temperature of the hot reservoir. I'm asked to solve for what is the temperature of the hot reservoir. So quite simply, if I just say, okay, temperature cold minus temperature hot is going to be 1 minus the efficiency. So now I can simply rewrite the temperature of the hot reservoir to be equal to the temperature of the cold reservoir divided by 1 minus the efficiency, or 293 divided by 1 minus 0.59, and I'm going to come up with 715 degrees Kelvin, or 442 degrees Celsius. So pretty hot. Okay, so here we have a block of ice that's falling into the ocean. The mass of the ice is going to be 4.5 kilograms. It's going to fall into the ocean, and I'm going to, for simplicity, I'm going to say it's 0 degrees Celsius in the solid phase. And how much energy does it take really just to melt that ice? So I'm just going to say it's going to go to 0 degrees Celsius in the liquid phase, more for simplicity. The temperature of the ice is going to be 0 plus 273 degrees Kelvin. Temperature of the ocean, temperature of the water, is going to be 3.5 plus 273, or 276.5 degrees Kelvin. We're asked, how much does the entropy of the world change? I know that entropy, this delta S, is going to be equal to the heat flow divided by the temperature, and the amount of heat flow is actually going to be the same for the ocean and for the block of ice. The heat is going to flow out of the ocean, it'll be negative, and it's going to flow into the block of the ice. The amount of heat flow is going to be how much heat does it take to change that ice from a solid to a liquid, so simply the mass of the ice multiplied by the latent heat of fusion for ice. The mass of the ice is going to be 4.5 kilograms. The latent heat of fusion for ice, you can take a second to look it up, is going to be 334 times 10 to the 3rd joules per degree Kelvin. So that's going to be equal to 1.5 times 10 to the 6 joules. And again, this will be negative for the ocean, and it's going to be positive for the ice. So we're asked, how much does the entropy of the world change? turns out that since the ocean and the ice are operating at different temperatures, the amount of entropy is going to be different. So the amount of entropy for the block of the ice is going to be at Q, it'll be positive, divided by the temperature the ice is operating at. So 1.5 times 10 to the 6 joules divided by 273 degrees Kelvin, and we're going to get 5.49 times 10 to the 3rd joules per Kelvin. That's the entropy of the ice. The entropy of the ocean water, now this is going to be negative 1.5 times 10 to the 6 joules. The ocean is operating at 276.5 degrees Kelvin, so that's going to be negative 5.42 times 10 to the 3rd joules per Kelvin. Now the amount of entropy change of the world, of the universe, is simply going to be, the sum of those two. So 5.49 times 10 to the 3rd joules per Kelvin minus 5.42 times 10 to the 3rd joules per Kelvin. And the change in entropy of the world is going to be 70 joules per Kelvin. We expected this to be positive, it'll always be positive, and we expected it to go up because we expected it to be non-zero because it's an irreversible process. Okay, last problem here is going to be using a PV diagram to calculate all these heats, all the works, and all the changes in internal energies. And at the end of the day, we're going to come up with the thermal efficiency of the engine. Big long problem, lots of points, or lots of little bits to do. Also mean that it's worth a lot of points, but really each one of these points is not too awful bad. It's just going to be a lot of writing. So I've gone ahead and I've written out everything that we know from the problem: 0.35 moles, diatomic gas, CV and CP, and I've read the temperature and pressure off of the PV diagram, converting this into pascals. That's going to be 10 to the 5th right there. So the very first thing we need to do is figure out what the pressure and the pressure and volume is at all the various points. So part A says what is pressure at 2 and volume at 1, volume at 2, volume at 3. So let's just go ahead and start off at point 1. We can say the old PV is equal to nRT, point 1, point 1, point 1. So we can say that the volume at 1 is going to be equal to N times R times T1 divided by P1, or 0.35 moles, 8.315. But we got the temperature, we just read that off as 300 degrees Kelvin, and the pressure is going to be 1.013 times 10 to the 5th pascals. So V1 is going to be equal to 8.62 times 10 to the minus 3 cubic meters. I can go ahead and say, oh look, point 1 and point 2 are going to have the same volume, so I've solved for V1 and V2 right here. Now I can say, okay, this is going to be a constant volume process, so I can say that the pressure at 1 multiplied or divided by the temperature at 1 is going to be equal to nR divided by V. That's going to be a constant. That's going to be the pressure at 2 divided by the volume at 2. So I can use this to solve for the pressure at point 2. Pressure at point 2 is going to be equal to the pressure at point 1 multiplied by temperature 2 divided by temperature 1. So that's going to be equal to 1.013 times 10 to the 5th pascals. Temperature at 2 is going to be 600 degrees Kelvin. Temperature at 1 is going to be 300 degrees Kelvin. So I've got my pressure at 2 now to be equal to 2.03 times 10 to the 5th pascals. Lastly, I need to solve for volume 3. I've got the other two volumes. I can use the fact that I know that everything I need to know about point 1, so I can say that the volume at 1 divided by the temperature at 1 is going to be equal to nR, that's an N, divided by the pressure. Going from 1 to 3 is going to be a constant pressure process, so that's going to be equal to a constant nR divided by P. So that's going to be volume 3 divided by temperature at 3. So I can say volume 3 is now going to be equal to volume 1 temperature 3 divided by temperature 1. I know that the volume at 1 is going to be 8.62 times 10 to the negative third cubic meters. I know that the temperature at 3 is going to be 492 degrees Kelvin. The temperature at 1 is going to be 300 degrees Kelvin. So I'm going to come up with 14.1 times 10 to the minus third cubic meters for point 3. Now that I've filled up that slide, I've gone ahead and I've written down all of my pressures and volumes up here simply to save on space. Now we're going to use these to solve for part B, the heat, the work, and the change in internal energy for each one of these processes. We'll start with process 1 to 2. That's going to be a constant volume process, so delta V is going to be equal to 0. That tells us that the work is going to be equal to 0. So I've got the first one. If I'm interested in the heat, that's going to be a constant volume process, so that's going to be the number of moles specific heat at a constant volume, change in temperature, and now I know these change in temperatures, so I can say that the heat flow is going to be equal to 0.35 moles. My CV is going to be equal to 5/2 multiplied by 8.315, and it's going to finish at 600 degrees Kelvin, and it's going to start at 300 degrees Kelvin. So the heat that flows into the system is going to be equal to 2180 joules. Lastly, I know that delta U is going to be equal to the heat flow minus the work, the first law of thermodynamics. Work is equal to 0, so my change in internal energy is also going to be 2180 joules. So we've got that process out of the way. Now let's look at the next process, process 2 to 3. This is going to be an adiabatic process, so what that tells us is the Q is going to be equal to 0. For any of these processes, I can write the change in internal energy is going to be equal to N times the CV delta T. So for this is going to be 0.315 moles. I'm sorry, 35 moles. CV is going to be equal to 5/2 times 8.315. Now in this case, it's going to go from 490, it's going to finish at 492, and it's going to start at 600. So the change in internal energy is going to be equal to negative 780 joules. Now I can use the first law of thermodynamics. Delta U is equal to Q minus work. I know Q is equal to 0, so I can simply go ahead and write my work to be equal to Q minus the change in internal energy. So it's going to be plus 780 joules. Lastly, let's take a look at the process from going from 3 to 1. This is going to be a constant pressure process. So the easiest thing to solve for is going to be the work. The pressure multiplied by the change in volume. Pressure is going to be a constant, 1.013 times 10 to the 5th pascals. The volume is going to finish at 8.62 times 10 to the minus 3 cubic meters. It's going to start at 14.1 times 10 to the minus 3 cubic meters. The amount of work done is going to be equal to then negative 560 joules. So now I have the work done. I can solve for the heat flow for a constant pressure process. That's going to be equal to N multiplied now by the heat capacity at a constant pressure multiplied by the change in temperature. So 0.35 moles. Now it's going to be my 7/2 multiplied by 8.315. The change in temperature, it's going to finish at 300. It's going to start at 492. So the heat flow is going to be equal to negative 1960 joules. And lastly, I can say that the change in internal energy of the system, using the first law of thermodynamics, delta U is going to be equal to the heat minus the work done by the system. Go ahead and say that's negative 1960 minus negative 560, so negative 1400 joules is going to be the change in internal energy of the system. Okay, now that we've done all the hard work, we can solve for the what we're really interested in, parts C, D, and E. I've compiled what I had on the last slide here in a somewhat readable form. So first, for part C, let's find the net work that was done. So the net work done is simply going to be the sum of all the work 1, 2 plus work 2, 3 plus work 3, 1. They're written up there in that table. 1, 2 is going to be 0 joules, work 2, 3 is going to be 780 joules, and work 3, 1 is going to be negative 560 joules. So you add all those bad boys up, and we're going to come up with 220 joules. That's going to be the net work done by the system. Let's also take a look at the net heat flow into the engine. So it's going to be the same thing. Q net is going to be equal to Q12 plus Q23 plus Q31. Just kind of making an aside that Q12 is positive, so this is going to be QH, that's going to be the heat flow into the system. Q31 is negative, that's going to be the heat flowing essentially out of the system, that's going to be QC, and this guy here is actually just going to be 0. So now that I've made that clarification, QH is going to be 2180 plus 0 minus 1960, and that's going to come up to, not surprisingly, negative 220 joules. The internal energy of the system hasn't changed, so these two should be the same but negatives. So what is the thermal efficiency of the engine? I know that the efficiency is going to be equal to the net work that it did divided by the heat you had to put into it, which is going to be 2180 joules. So that's kind of the tricky part about part E. So the net work is going to be 220 joules, QH is going to be 2180 joules, so the efficiency is going to be 0.101, not very efficient. We're asked to compare this to the efficiency of a Carnot engine, which is going to be the most efficient one that we could possibly have. Operating at these two temperatures, the efficiency is simply going to be 1 minus the temperature cold divided by the temperature hot, and I know what these temperatures are. The temperature cold is going to be 300 degrees Kelvin, efficiency is going to be 600 degrees Kelvin, and I'm going to come up with 0.5 for the efficiency of the Carnot cycle, much more efficient than this engine right here.